From the JAMA Network, this is the JAMA Medical News Podcast, discussing timely topics in clinical medicine, biomedical sciences, public health, and health policy featured in the medical news section of JAMA.
I'm Kate Schweitzer, the Associate Managing Editor of JAMA Medical News. More and more, antimicrobial resistance, or AMR, has become labeled a silent pandemic. It's emerged as one of the top global threats facing humanity, one that researchers predict will claim 39 million lives over the next 25 years. Yet it hasn't garnered much awareness among the general public or even among sectors outside of public health. This past fall, those leading the effort to decrease AMR convened for a high-level meeting at the United Nations and, among other targets, called for a One Health approach. It's a strategy that encourages disciplines beyond human healthcare, such as agriculture, animal health, biopharmaceuticals, and wastewater and the environment, to join forces to improve practices and innovate solutions. While promising, coordinating efforts across multiple fields to address this crisis has not been easy. A historic lack of antibiotic stewardship has prevented optimal health outcomes, and limited incentive to develop new antibiotics to replace those medications that are no longer effective in treating infections has only accelerated resistance. With AMR mitigation yielding a low return on investment, efforts have waned and research has stalled. This slowed pace of progress has underscored an urgent need for a new path forward. Following an optimistic report on future technologies to counter AMR, the engineering community stands to serve as the next critical One Health collaborator. Leaders of the Engineering Research Visioning Alliance, also known as ERVA, believe engineering-directed research can bridge the gap between fundamental principles and the tangible, scalable tools that patients and clinicians can actually use. ERVA, an initiative funded by the U.S. National Science Foundation, gathered 55 multidisciplinary experts to create a roadmap of less explored engineering-based opportunities to advance efforts in ending AMR. They identified 5 key priorities, spanning the development of diagnostic wearable devices, antimicrobial surfaces, and drug-free treatments. The goal? To inspire researchers to support these ideas and funders to invest in them. I'm joined today by Dr. Anita Shukla, the Elaine I. Savage Professor of Engineering at Brown University. Her research has focused on designing responsive, targeted biomaterials for applications in drug delivery and treating bacterial infections. And she proposed and chaired the ERVA Visioning event, which is what laid the groundwork for this AMR report. Anita, thanks so much for joining me today.
It's my pleasure, Kate. Thanks for having me here.
Of course. So the ERVA Visioning event convened in February of last year. What prompted you to get all these researchers, industry leaders, policymakers, all in a room together?
So antimicrobial resistance is a truly global health threat. And it's been known for some time now that we've entered this post-antibiotic era in which we really need new solutions to combat AMR. And this is an area I've worked in terms of my research for the last decade, a little bit more than a decade, actually. And I've started in that research identifying that engineering really could play a very, very big role in solving this AMR crisis. And that's what led me to propose holding an event where we truly just focus on the engineering opportunities that could have the largest impact on combating AMR using an interdisciplinary group of individuals that have expertise in this area.
And it does seem engineering holds the keys to combating AMR. What distinctive perspectives do you feel engineers have that can help with this challenge?
I think engineers are very skilled at identifying how to combine various aspects of science and technology together to come up with scalable solutions. And I think in that sense, engineering, all the way from a very molecular-focused engineering up to a more device-oriented engineering, can play a very big role in both preventing and treating AMR.
And before we dive into the potential solutions to come out of the event, what have you found are some of the biggest existing gaps in AMR research to date that engineers could fill?
So there are many, and our report really highlights these gaps as opportunities, grand challenges and opportunities, focusing on what engineers can do to make a difference in this fight against AMR. So I think we're going to end up talking about this a bit more, but those opportunities, those gaps are really identified in the report as 5 critical grand challenges that fall within 3 areas, which are prevention, treatment, and more modeling-based approaches.
Thanks, Anita. Can you speak more generally about those 3 distinct research areas?
Sure. So we talk about this a lot in the report, so I definitely recommend that your listeners go ahead and look at the report if they want a lot more detail. But we identified 3 key areas. One is this preventative measures, right? And we just talked a bit about that. Biosensors being an important aspect of this, being able to design biosensors that can diagnose a lot of different types of bacterial pathogens while being sensitive and stable is something that we talk about. How to integrate these into wearable technologies is something where engineers need to be involved in research in that area. Surfaces, again, how to make high-touch surfaces antimicrobial and do it in a scalable manner. Those are some of the aspects that are discussed. That's, again, in the category of preventative measures. Then we move on in the report to talking about novel therapeutic approaches. These are both development of new drugs, but really we emphasize development of the delivery systems for these drugs. There may even be existing drugs that would be more effective if they have good delivery systems that are responsive potentially to the microbes themselves, the bacteria being there in that environment. And so we talk about the importance of that. Also, cell-based approaches, so drug-free approaches, host-based approaches, so immunomodulatory materials and using kind of engineering of the immune system or host microbes to combat antimicrobial resistance and doing so in a stable manner. And finally, modeling advancements was the last thing. And by modeling, I'm talking about both ex vivo kind of cell-based models as well as computational models.
Let's talk about some of the specific tools and technologies that you've proposed in this report. Our inability to effectively diagnose pathogenic bacteria, as you said, was addressed. Can you walk us through the potential for those biosensors and wearables and get a little more specific into what that promise might look like?
Yeah, in the report, we talk about the diagnostic biosensors essentially in the future would have the potential to identify a broad range of pathogens. We focus a lot on bacteria in the report. Of course, we identified that fungal infections are also quite problematic, but bacteria was our primary focus in the event. And so having the ability to identify drug-resistant bacteria selectively and with sensitivity, that those are some of the things that are highlighted in this report. There's a need for that. Using a variety of biomarkers, identifying what those biomarkers would be to say that you have a drug-resistant infection, doing so in patient samples that might be available at low volume, for example. Designing biosensors that have good shelf life so that they can be used all over the world in low resource settings even is needed, and how to integrate these into wearable technologies for at-home diagnosis as well. That's what we've come up with.
Now, studies have shown how bacteria can attach to surfaces. For example, in clinical settings, 92% of privacy curtains become contaminated with bacteria within a single week, which contributes to hospital-acquired infections. The IRVA report also has a proposal for this. Can you elaborate?
Yeah, one of the areas that might be an opportunity to really dive into is the use of nanostructured surfaces that might prevent the attachment of bacteria to those privacy curtains or other high-touch surfaces that might be either in clinical or at-home settings. And really understanding how those surfaces interact with microbes is somewhere where engineering tools are needed.
And because engineering focuses more on practicality, it seems uniquely positioned to offer that trifecta, opportunities that are faster, cheaper, more accurate. This feels especially apparent in its role in revolutionizing computational modeling, which you mentioned earlier, compared with costly, time-consuming in vivo experiments. It could be a really viable option. What's your perspective on this?
Absolutely. I think computational modeling advances are going to be a really, really important part of this. And you mentioned it yourself that ex vivo experimentation or in vivo experimentation is very costly and time consuming. Computational models make it so that it's not necessary to have a lot of the challenges that come up in those ex vivo and in vivo scenarios will not necessarily come up in the computational models. It's difficult to do everything with the computational model. But I do think they'll play a very large role in advancing the technologies that we propose in this report as engineering opportunities, research opportunities, in advancing those, validating those new technologies that will come out of the research that is done, computational approaches will play a big role in that.
Can you walk us through the other future technologies highlighted in this report?
Sure. We've talked about the two that we've already discussed are the biosensors and antimicrobial surfaces. Perhaps we didn't touch so much on smart biomaterials. So smart biomaterials is a really interesting opportunity, and it can be broken down all the way from smart drug delivery systems to take our existing or new antimicrobial therapeutics to take them forward and make them more effective against antimicrobial resistant bacteria, or make them so that they are not causing AMR development. Those smart delivery systems that can really modulate the delivery of therapeutics will play a big role in that. In addition to that, smart biomaterials, we're also talking about opportunities in developing immunomodulatory materials, materials that can actually get your immune system to fight those resistant bugs and lead to better outcomes in treating drug-resistant infections. We also talk about other drug-free approaches. So engineering your immune cells again, also engineering commensal microbes. We all have bacteria within us, right, that are actually many times very, very beneficial to the way the body functions. You need your host microbiome. How can you actually engineer commensal microbial cells, commensal bacteria, to help fight antimicrobial resistance? This is an opportunity for engineers as well. And finally, those modeling approaches, which we also touched on. We talked about computational approaches. Ex vivo approaches will also be very important. And this involves taking, for example, cells from a patient along with bacterial cells, whether from a patient or not, and combining these into complex models of infection that you can then use outside of a living system in order to validate new solutions.
Most of these concepts are years, if not decades out. How close are we to seeing these technologies in use?
We talked about that a lot in our visioning event. What is actually, 5 years out versus further than 5 years? That's kind of how we framed our discussion. And I can give you an example. With the biosensors, what we thought about is that there's a lot of advanced tools now and ability to study biomarkers that might be associated with certain drug-resistant infections. If we can identify those, that directly aligns with sensor development. You need to know what you want to detect before you develop a sensor to detect it. And we believe that there can be some good research done within 5 years on identifying what would be good biomarkers to go after for selectively saying that you have this drug-resistant infection. However, after that, development of sensors that are stable in a broad range of environments, potentially could be integrated into a wearable sort of technology, that may take much longer than 5 years.
There seemed to be hope that eventually the benefits could be far-reaching, that we might be able to perform at-home testing for bacterial infections, just as we do with COVID-19, or that antibiotic shelf life would vastly improve over the current expirations for these medications. What might we expect longer term?
Yeah, absolutely. I think long term, you could imagine that the privacy curtains that you were talking about earlier, or my doorknob, for example, into my office, might have nanostructured solutions on them that are cheap and work in a reproducible manner over long periods of time, because we've now had engineering advances that can lead to developing these sorts of surfaces that could be applied to a broad range of materials. So you could imagine that years down the line, we'll be able to really prevent the spread of AMR using these sorts of materials.
Right. And this IRVA visioning event was certainly a first step. What do you see happening next?
I think next is for people to read this report, understand that AMR is a big problem, and to try to inspire individuals that have the right skill set to really enter this area. There may be many, many people that are working on other technologies but have the right skill set to come in and work on the research opportunities that we've identified. We want them to know that we need those individuals in that line of research. And so in addition to researchers working in this field, potential funders to prioritize this type of research. Those are the next steps.
And up until now, the AMR charge has been predominantly led by healthcare and pharma. How best can the medical community and engineers collaborate to have the greatest global impact?
That is a terrific question. So our event actually brought together clinicians as well, veterinarians as well as engineers and other scientists. And there has to be more events like this that bring together these sorts of individuals to really try to come up with the solutions guided by the opportunities that we've discussed. And I think people being able to kind of understand what is important to each set of individuals, what the different skill sets are that are involved, and have a open conversation about the technologies that need to be developed. I think that's the next step. But it is very, very important for people to work together. And even more broadly speaking, we could talk about how there might be changes to educational practices as well, trying to train more interdisciplinary engineers going forward, as well as more interdisciplinary clinicians going forward, those that are more aware of what engineers can do, and engineers that are more aware of what the clinicians can do, and how we might be able to work together. So starting very early with my own graduate education in chemical engineering, although as a traditional chemical engineering department, we did a lot of interdisciplinary research. And that kind of became something where I started to see that it doesn't matter whether you're a chemical engineer, electrical engineer, mechanical engineer, you can apply these engineering skill sets to a lot of different problems, whether that's healthcare or something else.
That's good to hear. Still, the number of AMR researchers has been declining for more than 20 years. It's estimated that 3,000 AMR researchers are active globally compared to about 46,000 for cancer. Considering you've been dedicated to antimicrobial resistance-related research for so many years now, what do you see as necessary to ensure that this research is prioritized, that it's pursued?
Awareness, first of all, of the problem is critical. And understanding that maybe it's not an immediate thing that you're seeing as impacting your life right now, but it really truly is impacting us in many, many different ways across a variety of sectors. Having that realization, and then again, funding agencies really need to come forward, whether public, private. We need research funds in this area to tackle these amazing opportunities that we've outlined in our report. There's no way to do this without good resources. I also wanted to emphasize that engineers really have an opportunity to lead to solutions that are more cost effective. So the fact that there's this low return on investment, I think engineers could make a difference there. We potentially could be doing a lot of this development at a much lower cost than we have been for traditionally doing this, right? Using computational models, ex vivo models to validate our findings. That's another opportunity.
And how is it that engineers are so well suited toward this level of efficiency that they're the ones to answer the call?
I think this comes down to our fundamental education, the way engineers are trained. We do actually think about a lot of those aspects very early on in our training, even as undergraduate students. We often take classes in economics. We learn about optimization, and that's part of our design training as well that we receive. So it's kind of ingrained in the way that we are thinking about technologies all the time.
That's it for this episode of JAMA Medical News. Thanks to my guest, Dr. Anita Shukla. I'm Kate Schweitzer for JAMA Medical News. This episode was produced by Daniel Musisi at the JAMA Network. To follow this and other JAMA Network podcasts, please visit us online at jamanetworkaudio.com. Thanks for listening, and join again next time.
This content is protected by copyright by the American Medical Association with all rights reserved, including those for text and data mining, AI training, and similar technologies.